Imagine a digital assistant that doesn't just follow your instructions on one app or one screen, but adapts seamlessly as you switch from a mobile phone to a desktop, from a low-resolution display to a 4K monitor, or from a social media app to a complex design tool. This isn't science fiction. It's the future of GUI agents, and we're finally building it. But here's the problem. Today's GUI agents are trained on static datasets. They learn how to click buttons, find icons, and parse text on fixed interfaces. But real-world digital environments, they're in constant flux. New operating systems roll out. Apps update their layouts. Screens evolve from 1080p to 4K. These aren't minor tweaks, they're fundamental shifts in how interfaces are structured, how elements are scaled, and where interaction points appear. And when that happens, current agents fail. They don't adapt. They forget. They overfit to the coordinates and scales they learned before. Their grounding, the ability to map language to pixels, collapses. So we ask, what if GUI agents could learn continuously, just like humans do? That's the core idea behind Continual GUI Agents, a new task setting that models real-world GUI dynamics through two evolving challenges, domain-in-flux and resolution-in-flux. Let's break that down. When you move from a mobile OS to a desktop or web application, the entire interaction paradigm changes. Mobile interfaces are text-heavy, with vertical scrolling and gesture-based navigation. Web apps rely more on icons, menus, and hover interactions. These aren't just cosmetic differences, they redefine where and how users engage with content. Similarly, when resolution shifts, say from 1080p to 4K, everything scales. Text sizes change, button positions shift, and visual proportions distort. A button that was perfectly centered at 1080p might be off-center at 4K. And if your agent is trained only on one resolution, it won't know what to do. This is where most current methods fall short. Supervised fine-tuning, SFT, memorizes specific layouts. It's great for static tasks, but terrible for change. Reinforcement fine-tuning, RFT, does better. It uses on-policy rewards to guide behavior and minimizes KL divergence from a reference model, which helps prevent catastrophic forgetting. But even RFT has a blind spot. It optimizes for current task performance, not future adaptability. It rewards accuracy, but not diversity. It doesn't care if the agent learns to generalize across locations or scales. It just wants the right answer now. So we introduced GUI-Anchoring in Flux, GUI-AiF, a new reinforcement fine-tuning framework that explicitly teaches agents to anchor in flux. How? By reshaping the reward signal. GUI-AiF introduces two novel rewards, anchoring point reward in flux APR-iF, and anchoring region reward in flux ARR-iF. APR-iF encourages agents to explore diverse interaction points. For a single instruction, instead of generating one bounding box, the agent generates multiple predictions. We calculate the center points of each, compute their spatial variance, and reward high variance, meaning the agent is exploring different regions of the screen, not just locking onto one fixed coordinate. Why does this matter? Because in a shifting domain, say from mobile to web, the correct interaction point might be in a completely different part of the screen. By rewarding exploration, APR-iF ensures the agent doesn't get stuck in a single location. ARR-iF takes this further. It rewards diversity in predicted element regions. Instead of just checking if the box is close to the ground truth, we model each predicted region as a Gaussian distribution, capturing both center and scale. Then we compute the Bhattacharya distance between these distributions to measure how far apart the predictions are. High separation means the agent is generating region predictions that are spatially distinct, which helps it handle scale variations across resolutions. Whether the interface is 1080p or 4K, the agent learns to recognize the same element, even if its size has changed. Together, these rewards create a powerful counterbalance. While the standard RFT reward pushes the agent to get the current task right, GUI-AiF's rewards push it to stay flexible, to explore, to generalize, to adapt. And the results speak for themselves. On the screen spot V1, V2, and Pro benchmarks, GUI-AiF consistently outperforms state-of-the-art baselines, including SFT methods like C-click, and advanced RFT models like GUI-G2 and SEGUI. In continual domain learning, moving from mobile to desktop to web, GUI-AiF achieves 83.5% average accuracy, beating the next best method by over 2 percentage points. And in resolution shifts, from normal to high-res, it surpasses all baselines, even when the others fail to adapt at all. But the real breakthrough isn't just performance. It's why it works. Our ablation studies show that removing either APR-iF or ARR-iF leads to measurable drops in performance. And interestingly, APR-iF has a bigger impact than ARR-iF, because domain shifts are fundamentally about location changes. When you switch from mobile to web, the layout transforms, interaction points move dramatically. But scale changes. They're secondary. We also tested forward transfer. Can agents use knowledge from earlier tasks to perform better on later ones? Yes, and dramatically. After training on mobile, GUI-AiF outperforms baselines on desktop and web. After training on normal resolution, it beats them on high-res tasks. This proves that by encouraging exploration, GUI-AiF builds generalizable grounding, not just task-specific memory. And critically, we found that removing the KL divergence term, the very component that stabilizes RFT, causes performance to drop. Why? Because uncontrolled exploration can collapse the policy. The KL term is the anchor. It ensures the agent evolves gradually, not chaotically. We also visualize the heat maps. On a web interface, a standard SFT agent fails completely. Its prediction is scattered, off target. A GUI-AiF agent trained only on mobile gets the right region, but with poor precision. But after continual training across all domains, the same agent refines its grounding, accurately locating the target based on the instruction. This evolution, from rigid to adaptive, from narrow to general, is the essence of continual learning. Now, of course, there are limits. We used a 3B model, 3 datasets and 3 benchmarks. The absolute performance is still constrained. But this is just the beginning. The real-world GUI landscape is far more complex. Layout changes, dark mode, language localization, dynamic UIs. Our work lays the foundation, a new task, a new framework, a new reward mechanism for building agents that don't just react to the world but learn from it. So what does this mean? It means we're no longer training agents for one interface, one device, one resolution. We're training them for a world that never stops changing. And that's not just progress, it's a paradigm shift. In closing, this paper introduces continual GUI agents, establishes the first framework for continual learning in GUI environments, and proposes GUI-AiF, a novel reinforcement fine-tuning method that stabilizes grounding through dynamic rewards. It's not just better performance. It's a new way of thinking about how AI agents can interact with the ever-evolving digital world. The future isn't static, and neither should our agents be.